Hi, everyone. Welcome to our um, second uh, uh, public science lecture for the semester. And tonight we have Professor Addie Dove from the University of Central Florida, who's going to be talking to us about dusty planetary surfaces. And please welcome Professor Dove.
Thank you. Get slides up. Hopefully you can see those now. Thanks for having me. I'm sorry I can't be there in person, but it is so far away from us here at UCF. But I look forward to coming out there sometime soon. So, hi everyone. I am Dr. Addie Dove. I am a planetary scientist and I am at the University of Central Florida in the Physics and Planetary Sciences group here. And my research, as I'll talk about today, really focuses on dusty planetary surfaces. So it's something I really like to talk about. A lot of the work I do is funded through the Center for Lunar and Asteroid Surface Science, which is a NASA-funded node. And then also we do work here at UCF in the Center for Microgravity Research, which is where we fund a lot of our fun experiments, some of which I'll show you today. But a lot of what I'll show you today is actually photos from spacecraft missions, and I had to start off. I usually, when I talk about dusty planetary surfaces, I mostly focus on the moon and asteroids because that's what a lot of my research focuses on. However, I couldn't let the great opportunity to show a movie from Perseverance. I couldn't let this opportunity pass me by. So here we have the landing of the Perseverance rover. If you all missed this, I'm very sorry. You should go and watch this full video on YouTube. But Percy recently landed on the Martian surface, and when it did so, it returned this amazing first time ever video of this rover landing on the Martian surface. So the way Percy landed was actually similar to the way the Curiosity lander landed several years ago, but we didn't have video of that at the time. There was some still camera from afterwards, but we didn't actually have video of the landing. So I will replay that a little bit. And I'm just playing the final part of the sequence here because it's highlighting some of what I'm going to be talking about today, which is that planetary surfaces are covered with lots of fine, dusty material. Mars is a little bit different because Mars, like Earth, has an atmosphere, and that actually makes things very complicated. Not that asteroids and the moon aren't complicated, they're just complicated in different ways. But as you can see, as the rover is coming close to the surface here, the sky crane has these engines that are firing to hold the rover up as it slowly gets lowered down. You can see the up looking view on the left shows those little engines that are firing. And they're creating this crazy, swirling, dusty debris all around the rover. Curiosity was actually probably damaged a little bit from some of these rocks that you see flying up in this image, but we learned lessons from that mission, and it seems like Perseverance had a very nice landing, although you can see there it totally gets immersed in a swirling cloud of dust. So one of the challenging things of any planetary exploration is that most surfaces in the solar system are solid surfaces, at least, are going to have dust on their surfaces. And so as we move on and explore other places in the solar system, we have to understand what those surfaces look like, what they're made of, and how we interact with them. We learn lessons every time we go to new places and we send new rovers and new spacecraft. And some of those lessons are learned just by going there, but there's a lot of research we can do here on Earth and in our labs and in theory and modeling to understand these things as well. So today I'm going to talk a lot about dust, and sometimes I'll use the term dust, sometimes I'll use the term regolith. And so I have to have this obligatory slide that sort of explains those things a little bit. So dust covers a lot, as I said, dust covers a lot of surfaces in the solar system, places like the moon, asteroids, other moons of other planets, and Mars. And dust is usually the finest part of asteroid or lunar regolith, where regolith is just the soil that builds up over time. So it's broken up bits of rock that cover the surfaces of the moon, etc. So you can see here, right, we have on the right-hand side, this classic image of a boot print from an astronaut walking on the surface of the moon. And the surface was just this really fine powdery dust. And you can see the boot print is in really stark relief. And that's because of the way this material behaves. It sort of sticks together and is very cohesive. When we get to larger scales, you can see sometimes we have boulders and rocky things. The regolith is just formed by the fact that these surfaces are in space and they're being bombarded with rocks from other places in space. It just builds up over time. And so all of these surfaces are actually really complicated. Like, oh, it's just dust. But these actually really complicated rocky surfaces that we're planning on exploring, and we are exploring. And one final clarification, dust is not the dust that's in your houses and all the stuff that is built up on your surfaces. And I'm sure it isn't. I'm sure everyone's houses are perfectly not dusty. But if they are, it's a different type of dust. So you can see here this lovely image on the right. Dust in our houses and dust we usually talk about is actually like a lot of organic material. So a lot of fuzzy stuff and not fuzzy stuff that is biological and I don't study. And the really cool microscope image though on the left shows that it's actually dust. Household dust is also really complicated and it's made up of a lot of different things. But that's not what we're talking about today. So our dust that we're talking about is just broken up bits of rock that are going to be really jagged potentially, but it is not the dust that's definitely not on my computer screen, for instance. But dust is everywhere. It's ubiquitous, and it's everywhere on every surface we look at. So, and it's also hazardous. So we really need to understand it. So these are some pictures of surfaces, additional pictures of surfaces of asteroids. The one on the left is called Itokawa. The one on the right is from the asteroid Eros. And both of these images are from spacecraft missions. So we have images of places like asteroids, of the moon from Earth-based observations. But most of our best images come from actually sending spacecraft to these bodies to get up close and personal images. And we'll look some more at those as we go along. Itokawa, you can see here, is a relatively small asteroid, only 540 meters in the long dimension, but it has all of this really crazy structure and shape all over it, where there's some really big boulders, there's some areas that look really smooth. And the Japanese Hayabusa mission went to this asteroid and returned this image and lots of others, and actually went to the surface and got a sample. The asteroid on the right, Eros, is a bigger asteroid. And so you can see here, this is a more zoomed in image on the surface. And there was a spacecraft mission called the NEAR mission that returned images from Eros. And then finally, we're looking at these big grand pictures of asteroids that are on all sorts of different scales, or the picture of the moon, right? These are on much, much larger scales. If we look and zoom in at the really fine scale on these surfaces, what we find is things like this little weird shaped thing in the left, bottom left. So if you go somewhere like the beach, which if you're here in Florida, just step outside, right? The sand on the beach is kind of like what we're talking about on these surfaces. It's just lots of different particle sizes and it's been built up over time, except beach sand and most of the things we have here on Earth are exposed to wind and water that sort of makes them rub against each other and break down over time and sort of round. So you get much more sort of uniform or at least less jagged surfaces on those particles. However, this is an image of an actual lunar dust grain returned from the Apollo missions. And you can see that it has this really, really complex structure. So the rocks on these planetary surfaces are broken up through different processes, a lot of which are impacts, and we'll talk about some of those processes. But a lot of them are just due to impacts. So you just break up rock, and when you just break it up, you get some really interesting structures that form. And then there's nothing really to come along. There's no wind, there's no water to come around and round these grains or smooth them out. So you get these really interesting structures with different nooks and crannies. You get little stuff sticking onto bigger stuff. It's really complicated structure. And so we can take these really big images of the whole planetary body and try to understand what's happening to shape these images and shape these surfaces we see based on knowing that there's these weird little grains that are causing some of these surface features. And we can look at some other features on surfaces as well. If we talk about things like comets, it gets a little bit more complicated because on comets you have a lot more icy processes that can really change the structures of the surfaces. And there you can get a lot of things like little outgassing events that eject material into space. Although we think we maybe are seeing that a little bit on asteroids too, to a smaller scale. And on comets, you also get a lot of really interesting structures that form as the ice melts away and you get cliffs and things like that that form. You can get things like landslides on places like comets and on places like asteroids. So on comets, it's maybe a landslide that's kind of like a lot of things here on Earth where you have ice and things melting and your stability goes away, so the material slides out. But on asteroids, we can have that too, where maybe there was some sort of shaking due to an impact or due to tides pulling something, and it makes landslides on surfaces. So there's a lot of really interesting features we see on all of these surfaces that are a result of their history in the solar system and also just this complex surface processes that are happening. So this is my only slide with a lot of words, I think. But the first two things sort of summarize what I've said a little bit so far, which is that we see this really complex topography on surfaces. And so in the top left, you can see a zoomed in version of that asteroid Itokawa, where even the sort of smooth region, as the closer you zoom in, it's still really complicated. And this is something we've seen a lot with the new images from asteroids Bennu and Ryugu, where the closer you get, it's like it still just looks complicated as far as you go down. And so we really want to understand not only these surfaces, but also the whole planetary body. So the whole structure of these asteroids and how they form and how they evolve. One of the complicated things, and when we look at the next few slides, we'll talk about this a little bit more. But some of these planetary surfaces, other than Itokawa here, but are actually they're big solid rocks that are just sort of changed on their surface. So like when we think of the moon, it's mostly a really solid body that has the surface bombarded by meteorites that change and make the regolith on the surface. But some things like Bennu and Ryugu that we'll get next are actually probably just complex rocky stuff all the way down. So they are what are called rubble piles, where you just have the sort of smushed together bits of rock that are sort of loosely bound, but could be disrupted much more easily. And so, as I've mentioned, there's a lot of different processes that create these surfaces, that create these bodies. A lot of them are due to impacts. So if you're a planetary scientist trying to explain something in the solar system, a lot of times you're like, well, it was probably an impact. How did it happen? How did it form? It was probably an impact. It's always a good, safe explanation. But also there's other smaller effects that can happen on surfaces like vibrations. We've detected moonquakes, for instance, and now Mars quakes. Things like landslides I mentioned. There's also even smaller effects that are due to what's called electrostatic motion. So this is due to charges that build up on surfaces and the fact that they exist with electric fields in a plasma environment. And then also things like thermal cracking. When you have a surface that's exposed to heat and cold in cycles, you can get rocks breaking up due to that. So I'm not going to talk about all of those things today, but these are actually really complex surfaces. Even though you're just like, oh, it's a big rock in space, these are actually really complex surfaces that are changing and evolving over time. So let's start off with looking at some of these asteroids up close some more. And the two I'm going to talk about a little bit here are just because we've had recent spacecraft missions to these planetary bodies, and they have fun pictures and videos that we can look at. So here we have two asteroids that have recently had missions. On the left is Bennu, which has been the target of the OSIRIS-REX mission. And then on the right is the asteroid Ryugu. which it was the asteroid that the Hayabusa-2 mission went to. So I mentioned Hayabusa-1 went to Itokawa. More recently, Hayabusa-2 went to Ryugu. And one of the shocking things about these two asteroids, so these are both really small asteroids, but one of the shocking things is that they have very similar shapes, right? So we can see them here side by side. They sort of have this weird top shape where you sort of expect a thing to maybe be round, but if it's spinning, it can get this weird equator, an equatorial ridge. And they both have these really rocky surfaces where you can see maybe it's kind of smooth in some areas, but then there's some boulders. And they have these really interesting but very similar shapes. We knew going to these asteroids that they would sort of be shaped like this. We had some what are called shape models based on radar data from Arecibo, for instance. But getting up close and personal with them really revealed what they looked like. And so if we first look at Hayabusa-2 and Ryugu, here's that same image even closer. You can see there's this nice crater, for instance, on the one on the left. There's some big boulders on bits on the right, but it's this weird craggy, rocky surface. And this is one of those asteroids that's probably what's called a rubble pile. So it's just sort of smushed together, but there's not like one solid body on the inside. It's just all sort of held together through sticking forces and a little bit of self-gravity. So Hayabusa-2 explored Ryugu. It took images of the surface, and it actually sent a couple of little landers down that took some images at the surface, and then it actually also gathered some samples. So here we see some pretty cool images where we have the sort of target site where Hayabusa-2 decided to land and take some samples. This image on the right is one of my favorites because it's a super cool image of a spacecraft taking an image of another planetary body, but you can see the shadow of the spacecraft on the surface of Ryugu here. So the sun was behind the spacecraft in this picture, which is illuminating the surface nicely, but then you can also see the shadow of the spacecraft. So it's super cool. And there's an artist rendition of it then on the bottom there. So Hayabusa-2, like I mentioned, actually went to the surface and took a sample, and it did it not once, but twice. And it has since returned those samples to Earth. So they landed in the desert in Australia in December, I believe. And the royal we, not me personally yet, are starting to analyze those samples of an asteroid now. So these are some of the pictures that were taken from closer to the surface of Ryugu. The one on the left was taken by an orbiting image, but the one on the right was actually taken by this little sort of CubeSat small spacecraft-sized lander that had a brief stint on the surface. It looks very sort of underwater to me, but it's just because a little bit of the way the image processing happened and the lighting there. But you can see that even though the surface sort of looked smooth in some places from further up, it's very craggy, and it looks like there's mostly these bigger rocks on the surface, and there's not a lot of this really fine material. So this was a really big shock to most planetary scientists because when we'd seen these asteroids from spacecraft data and from afar, all of our data told us there was probably really fine material on the surface. And like going to the moon, we know that it's covered in this really fine, dusty material. That's what the boot prints showed us. That's what all of our data shows us. So we got there, and it was actually far more rocky and complicated than that. And we're still working on models to explain that. It seems like part of it is just that these rocks are really light and fluffy, basically. So they have some different heating properties. But then also, it's likely that some of the really fine material has maybe sort of worked its way underneath the surface or has been ejected from the surface. And you're left with this bigger stuff as a layer on the surface of the asteroid. So OSIRIS-REX then, I thought I had my video next, but I'm going to save the videos for after this. So OSIRIS-REX went to Bennu, and it is actually still at Bennu. It's returning from Bennu soon, and it has done its touchdown maneuver. But similarly to Ryugu, Bennu has this really complicated, craggy surface, and it's got these big rocks that are not what we expected. And so they were very challenging for the spacecraft mission. But both missions have successfully touched down and collected samples, and are returning those to Earth for analysis, which is it's we have very few samples from other worlds, so it's super exciting to see these samples come back for analysis and to compare to actually pretty different asteroids, and what their composition is, what the dust particles are, sort of what the size distribution of these things are, as we bring it back. So now here we go. Here's some video. So this is a video of the first touchdown on Hayabusa-2, and let's zoom ahead a little bit. So first we see this is a video from JAXA, and it's a camera that is mounted on the little sampling mechanism you can see there that touches down on the surface, and then there's some little jets that sort of push the spacecraft back away from the surface. I'm going to replay that a little bit here. And you can see as it goes closer to the surface, it's very rocky there. It touches down a little bit. It barely touches it. It's actually, this is at 10 times speed and it's sped up. It's actually touching it really slowly, but as it touches it, it throws up all this material, right? And you can see the spacecraft shadow again there. Pretty awesome. But you can see there's stuff flying still around the spacecraft. There's all this material. This is actually a really gentle touchdown. It's sort of gently at a few centimeters per second touching the surface and then going away. But part of the reason you get all of this ejected material is a little thing that they're impacting into the surface to actually kick some material up to capture it in the sample collection mechanism. Part of it is there's some engines to push it away afterwards. But a lot of it is just that there's very, very low gravity on these asteroids. So these are tiny little bodies in space, and they have very little gravity. And so anything you do on the surface, if you sort of touch down, it's going to kick up a lot of material. It's sort of like if you throw something down in the ground here on Earth, you sort of get a lot of stuff that comes up. I don't know, if you're on a baseball field and you throw a baseball down really hard, you're going to kick up a lot of material. Kind of like that, except you just sort of have to gently drop your baseball on an asteroid and you're going to kick up a huge amount of material. So these are really complicated things, but we can look at this reaction and see, okay, where's all this material going? How much of it do we think we got? And what does it look like? They did go back and image the place where they made the crater from this impact, from this touchdown, and you can see that it looks slightly different on the surface before and after touchdown. So we can see that we modified the surface a little bit. So then Hayabusa-2 actually did a second touchdown. If I can go to the next slide, there we go. Did a second touchdown on the surface and got a second sample. So this is a very ambitious mission. You sort of think you have one, just bring it back, be safe. But they were like, we got room. We were pretty confident. So they actually did another sampling of where they'd made a crater from a different experiment. And so here we have a little video, again, showing, there's a lot of words here. Here we go. So a video showing the sampling mechanism and touching down on the surface. And so as it goes in, you can see that there's not really any of this really fine material. It's all these big blocky things, but maybe there's really fine stuff on top of all those rocks. But as it touches, again, it's a very gentle touch. It still kicks up a lot of material. You can see it sort of flying away. You can track some of these little rocks. And we can really learn a lot about what the surface is composed of, how strong it is, how much dust and how much bigger stuff there is on the surface, even from these videos, but especially from the samples that we bring back. Okay, so then finally we have OSIRIS-REX, which this image is really dramatic right now. But OSIRIS-REX also touched down. They called their sampling touch and go, or tag. So we tagged an asteroid. So here we have the sample collection arm again, going down to the surface. It does a little maneuver to correct. It touches, again, very, very gently. It doesn't look like it there, but it touched very gently. And I'm going to pause it real quick. You can see here as it's approaching the surface, there's sort of some rocks here. There's maybe some little fine stuff in between, but it's not really clear what we're going to get. The sampling mechanism from OSIRIS-REX sort of has a little canister in it and a little burst of air that helps get stuff up into the canister when it's touching the surface. But it's a very gentle touch. It's a very gentle burst of air. But again, these surfaces are so breakable and so little gravity that it's easy to make a lot of material fly up. So you can see it touches there, it brings up some material, and they think they got a lot. They basically filled up the canister. They actually had trouble closing this canister because there was so much material in it. So we got a lot of material that is going to come back in a couple of years from asteroid Bennu. So all of these videos were super cool if you're interested in spacecraft missions and if you're interested in the surfaces of other planets. But they were actually extra super cool to me because this is sort of some of the experiments I do. So we do a lot of experiments here that look at low velocity, so very slow impacts into planetary surfaces. And we do that sometimes here in the lab, sometimes in what's called microgravity. So in places like in a drop tower in our lab or on parabolic reduced gravity airplane flights, where we can sort of neglect gravity for a little while and see what happens when you have very low gravity and impacts. And we see that you can get exactly what we saw in these images from OSIRIS-REX and Hayabusa, that you get this really dramatic results, even with little tiny impacts into surfaces or little tiny jets into surfaces. So this is just a fun image that we have of an experiment where we were dropping an impactor into a tray of what we call simulant, so simulated regolith, in an experiment here on Earth. If you've taken a little bit of physics, or even if you haven't, if you've ever like thrown a ball, right? You know that when you throw something on Earth, you throw it up and it comes back down, and that's due to gravity. And so when we do these experiments here on Earth, you can see that there's these sort of parabolas or trajectories of the particles that we're tracing here. So we illuminated them with a laser, and you can see little particles moving, and they sort of go up and fall down. So we can do some experiments here on Earth to look at, okay, if you touch something on a surface, you throw up material, how fast does it move? How far does it go? But we always see these trajectories where it falls back due to gravity. So we can still learn a lot about it though, and about the energies needed and things like that. But then when we do other experiments in microgravity, we see things that look a lot more like what we just saw in on OSIRIS-REX and Hayabusa, where you get these much more straight line trajectories where once material is kicked up off a surface, it just leaves. And that's because it has these speeds that are high enough to get it away from this little tiny gravity on the surface. So we can do some experiments like this in our lab and on planetary to understand other planetary surfaces. So I'm going to show a couple of videos then from experiments we've done on parabolic airplane flights. So you maybe heard it called the Vomit Comet, Zero-G airplane. These are flights where you are weightless for about 30 seconds, and so we can do experiments in those times. Sometimes they do parabolas on the airplane that are sort of like an asteroid gravity, so you have a little tiny bit of gravity. Sometimes we do parabolas where we're weightless and free floating our experiments, so you have very, very, very little gravity on it. They do lunar and Martian parabolas sometimes too, where you feel like you have the same gravity as you would on the moon or Mars. So this is an experiment that I'll replay this video where we have just some quartz sand in a little tray here in the bottom, and we impact a marble into the sand. I'll drop it again. You can see here that we have nothing playing. There we go. Okay, so you can see here that you see sort of we have a little bit of gravity again. So even then you have this sort of ejecta that falls back down. If we then go to an impact where there's some sound on this one, where we have a more solid surface, we can actually make things impact the surface and then bounce off and not actually create a lot of ejecta. So we can do this at slow speeds or with really more solid surfaces. We can look at different types of experiments. So I'll replay that one more time. Maybe I'll do that. Replay this one more time so you can see this is with a lunar simulant, so it's really fine material. You can see things bouncing off the surface. And then if we go one more time, here we have an impact where you can see a little bit of material flies off if you ignore sort of the stuff that was already stuck to a different thing and flying in front of it. But you can see that there's a little bit of material that flies off here as we impact into the dirt. And these experiments are at very, very, very low speeds. So they're at like a few centimeters per second. So it's like if you dropped a marble from an inch above the surface of a table, for instance, you'd already be going as fast as these marbles are going when they hit. So very, very slow speeds, and you can still get stuff coming off in low gravity. So it's an interesting way to sort of explore these surfaces. And I'm super excited that we have all this data now from actual spacecraft missions to these planetary bodies too. Think that's the same thing. It's just going to keep playing it. Okay, there we go. So I've talked about sort of things touching down on the surface. Another way we can disturb the surface manually and with spacecraft is with landing on the surface. So we saw this during the Apollo missions where the landers came down and the engines from the Apollo missions blew up plumes of dirt. And so you can see on the top some still images of the lunar surface. And then as the lunar module was coming down, all of this material sort of blocking the view of the surface. And we've seen this happen with Perseverance now, right? So we showed that image at the beginning. We've seen this happen actually a little bit. You can see with the data from OSIRIS-REX, for instance, you can see when the engines fire. And then recently, whoops, too soon. So recently, the Chinese Chang'e 5 mission also landed on the lunar surface and had some cool video of it descending and having little plumes of dust. So you can see it moving down toward the surface. And then as it gets close, it does a little maneuver and goes down. And as it gets closer here, you can see there's these streaks of dust with its little tiny engine as it descends to the surface. So we have all these ways that we change the surface when we try to study it or when we land on it. And we can study some of these things in our lab as well. So we've done some experiments in our what's called a drop tower. So just a short experiments in our experiment here on the ground, where we shoot a little plume of air into some simulated regolith. So in this case, asteroid regolith, where it's sort of big chunky stuff. And you can see on the left is in 1G. So we just did it on the benchtop on the ground. And on the right is in microgravity. And you get very different results when you do these two things. Let's see if they actually play. Okay, so on the right, you can see these little fine particles sort of go up and then the big particles move. That's because we're doing a little burst of air into the surface and you can see the rocks fly up. We're doing the exact same thing in the experiment on the left, except that it's sitting on the bench. It's in 1 Earth gravity, and it just looks like nothing happens. So there's a really big difference between how things behave, how this dust and these grains behave on in microgravity on asteroids or on the moon than they do on the Earth. I think the next one I have is the same thing where on the left it's in 1G and on the right it's in microgravity, but here we did a bigger plume and you can see it sort of makes almost no difference on the left again, but then this giant sort of explosion looking thing on the right. So you get a lot of material flying up. So this is just to highlight again that there's these really big differences between how dust behaves on the Earth and how it behaves in microgravity. And we can do some cool experiments to understand that and interpret the spacecraft data that we get. Okay, so I could talk a little bit more about some of these other processes. I'm just going to quickly mention some others. So I mentioned at the beginning that landslides do change planetary surfaces and can change on dusty surfaces. You can see up here on the left, this is obviously on Earth because of all the green stuff. And we have a landslide that can be a really huge event here on Earth that can damage infrastructure and things like that. We also see these kinds of things on other planetary surfaces like the moon and on, you can see on the left on, I think, Ceres, an asteroid that has some icy stuff in it, where we see sort of landslides and mass motion that happen even without the effects of like wind and rain on the planet. So all of these things can change these planetary surfaces. We can do some experiments to understand landslides. I Just ignore that slide. But we can do some experiments to understand landslides on these other planetary bodies, and again, understand if they're going to be different in low gravity on asteroids and the moon than they are here on Earth. We have these sort of simple little experiments we've built and flown on parabolic flights that just have some dirt in a box, basically. Um, and we rotate the box in different gravity levels and see how steep of a surface you can get and when you start to get landslides. And we can use that to understand when landslides form, how it depends on gravity, how it depends on what materials you have in it. We also sometimes on the flights get really things we don't want, like negative G's, where the plane sort of corrects itself and it makes all the material fly at the top of your experiment box. But that's okay. It's data you can get and analyze for different things. So that's what's happening in this one. But we can look at different slopes that form. And you can see, if you think about sort of slopes that you see on hillsides here on Earth, it usually has a certain angle. We can actually get really, really steep slopes when we're in low gravity. So we can use that to understand what we see on other surfaces. And this is just fun to show what the parabolas look like when you're on the airplane. You can see this is a Martian parabola, so you have sort of low gravity, and then you have a lunar parabola, and then these are 0G parabolas. So it's kind of fun. It feels fun too. So, and I think the next slide is just a short little video of one of my students and me with operating this experiment on a plane. A couple of our students actually. So this is on the reduced gravity aircraft. You can see that sometimes you see a video of people doing these parabolic flights and they're like doing Superman and flying through a really empty plane. It's not like that on research flights. You're doing your experiment and you're usually there's a lot of people on there doing science and technology demonstrations to understand all sorts of different things. But you can see here that we have some different experiment chambers and we're able to do different experiments on different parabolas and really try to understand planetary surfaces in unique ways. So I actually think I'm going to stop and not go into too much more. I'm going to go to my last slide. Just because I don't want to introduce an additional topic at this point, but I want to wrap up just by saying that planetary surfaces are complex. We think a lot of times about like Mars and how complex it is because we send a lot of different rovers there. And it has its own challenges. So it has an atmosphere, it has a history of water and maybe water processes on the surface. But all of these other planetary bodies, the moon and asteroids and other small moons and small bodies, are really fascinating places to explore. And they're also really complicated. But studying them can tell us about the history of the solar system. It can help us understand where things are in the solar system and how we can explore them better. So these early robotic missions are really helpful for understanding that. They're helpful for us knowing if we want to send bigger robotic missions there in the future, how we can do that, how we can send humans to these places in the future, right? If you imagine trying to send a human to one of these asteroids, it's not like they can just walk on the surface. We're going to have to understand how these surfaces interact and behave. And so these missions to the moon that are going to be going on soon with robotic missions, and then these early robotic missions to asteroids are really great precursors to help us really start to explore more and understand the history of the solar system and how we can use different places in the solar system to help us explore as well. So on this final slide, I just have some pictures from some of our different flight experiments. I like to be able to show that we involve students in a lot of our research and just fun pictures of different places we've been. In the top center is Dave, Citronaut Dave, who's our unofficial/official space mascot. And he's actually been to space. He's there in a Blue Origin experiment where he flew to space and came back. so doing space experiments and space exploration is really complicated, but there's lots of really cool basic science we can do using experiments here on Earth and interpreting spacecraft data that'll help us understand these planetary surfaces. And then, real quick, final selfish plug for to check out our podcast, Walk About the Galaxy, which is a podcast I do with a couple of colleagues here at UCF, where we talk about all sorts of new space discoveries, as well as nerd news and Star Trek and all sorts of different things that are take our fancy. Um, so I think there's been a couple of questions so far, and I'm happy to take more. Thanks for listening so far.
All right. Thank you so much, Professor Dove. So we do have some questions. Thank you guys for sticking around. If you have any more questions, feel free to add them to the chat, and we'll also make sure to ask them. So the first question is from Chloe. Do you think the sample from Bennu will have any rocks that will be able to be used for radioactive dating?
Oh yeah, so that's a great question. So we often do radioactive dating to understand the actual age of a surface of a planetary surface, and we can do that to rocks that have certain isotopes in them. I suspect that there are plans to do some of that for the samples we've returned. Um, we know that Bennu and Ryugu have different compositions, so they have a lot of carbon materials and a lot of silicate materials, but they likely have things that we will be able to date and actually get actual ages for those materials. And that's a great question because understanding the actual age of the material on those surfaces is going to tell us a lot about how those asteroids have evolved and how long they've been around and how long that material has been around, and will tell us a lot about sort of the history of the solar system.
It's definitely like an exciting way to learn about our origins in here.
Yeah.
So the next question is coming from Brian Murphy. Do you expect dust distributions on Phobos and Deimos to be similar to that of equally sized asteroids? And if not, what would be different?
So Phobos and Deimos are two tiny little moons of Mars, and we don't entirely know their origin, but they are sort of asteroid sized, as you mentioned. Um, and they have surfaces that sort of look a lot like some of the asteroids we see. I think that so far, what we know, especially of Phobos, um, the surface is probably going to have a little bit more of the fine materials than the super rocky surfaces of Ryugu and Bennu. But I anticipate that they would probably be similar to other asteroids of that size. There's a number of missions that are interested in going to Phobos right now and sampling the surface. And we really get up close images to be able to see what they look like. For Deimos, it's really tiny, so I would pretty much expect it to have distributions similar to asteroids of its size. I could be wrong. That is my intuition. It's possible that I'm wrong about that because the formation mechanisms might be a little bit different, in which case they could have just very different surfaces.
Okay. The next question is coming from Keith Camp. So if you had whatever technology necessary, what would be your like the body that you would want to explore and get a return sample from?
Well, I have a very simple answer, which is actually the moon. We haven't done sample return from the moon since Apollo, and there's like all sorts of places on the moon that we haven't been. And there's lots of really cool robotic sample return missions planned. In fact, the Chinese mission that recently went and sampled the surface. But then there's a lot of cool human missions there as well. If I'm going to be a little bit more broad and a little bit more exciting, I think somewhere like Titan would be really cool. So Titan is a moon, an outer solar system moon that is pretty big, actually. I mean, it has an atmosphere, and the surface though is sort of, and it has these features that look a lot like Earth. So you see like things that look like riverbeds, and you see lakes. But it turns out that the surface is mostly rock made of water ice because it's so cold out there that you have ice is looks like rock. And the lakes are probably things like methane and ethane. So it's cold enough there that methane and ethane are a liquid state. So I think like a sample return from there would be super cool because we have a cool mission called Dragonfly planned to go to there, that will image the surface and things like that. But actually getting a sample back would be pretty amazing.
Yeah, I think Titan would get my vote too. I think that would
Yeah.
be really interesting.
Yeah,
Um,
it's interesting for completely different reasons. There's all this weird chemistry, but it's sort of interest. Yeah, it's pretty cool though.
yeah. I have a question. So
Sure.
you mentioned the Hayabusa-2 mission that had 2 touchdowns. Can you go a little bit, was that, I'm assuming that was kind of part of the plan that they were gonna touch down twice? And
Yeah.
kind of what inspired it and kind of how they managed to be able to pull that off.
Yeah, so the Hayabusa 2 mission it's amazing. So it had all of these different features. So not only was it the main spacecraft that did the touchdowns, but it also, and I showed a couple of pictures, had a couple of little extra instruments that it dropped off. One was called Mascot, and I'm forgetting the name of the other one, but little sort of lander things that plop down. It did an experiment where it basically sort of shot an impactor into the surface, and then imaged that, and then that was the place where they went and sampled the second time. Um, so it was sort of in the plans to be able to do two. Obviously, if one had worked and they thought it was really successful and they thought it would be dangerous for the mission, they wouldn't have done the second one. Um, but doing two allowed them to sort of get one that was sort of at the surface in one location, and then the second time they did it in the place where they'd already made a crater, so hopefully got a little bit deeper down in the surface, to get two different types of samples. And they were able to separate them, so they had a sample canister that was able to sort of like rotate, so you get different samples in different parts of the canister. um, I think part of the motivation also was that on the Hayabusa 1 mission, they were able to get a sample, but it was smaller than they had wanted. So this gave them a second chance, if they needed it, to get another sample. And actually, the OSIRIS-REX mission could have done another touch and go maneuver. They had the material to be able to do another maneuver if they thought the first one like didn't work and they didn't get enough stuff. But they got so much on the first one, and there was no reason to endanger the spacecraft, so they didn't go in for a second one.
All right. We have a
Yeah.
comment from Dr. Palatai. Hi, Shaba. He says, really cool talk. Thank you so much.
Hi, Chava. Thanks.
I also have a few, kind of another question.
Sure.
So, speaking for something that inspired me to get into astronomy, the Arecibo telescope, you mentioned it and its kind of its role in kind of shaping or mapping the shape of these asteroids. Do you want to say a little bit about that and the role it played and kind of what you hope they might be able to do in the future?
Yeah. Yeah. Sure. Yeah. So the Arecibo telescope, one of the big roles it's played recently, for a while now, but more recently has been sort of in what's called planetary defense. So really using Arecibo to understand the asteroid population that's out there. So we can do some of that with optical telescopes looking for things. But Arecibo has really unique capabilities to be able to sort of detect asteroids. So detect if there's a single asteroid, if there's like a little asteroid system. So Arecibo's detected some cool like triple asteroid systems where there's three little things orbiting each other. But it's also able to actually map the surface. So if you have an asteroid that's close enough, you can bounce radar off of it and sort of map the surface. And so that's what they had done with Bennu prior to the OSIRIS-REX mission going there. And from that, they sort of built what's called a shape model. So an idea of what the surface looks like. It's the kind of thing that like then if you have a 3D printer, right, you have a shape model and then you 3D print that thing. But so they built a model of what that surface would look like, and the model they built even included like they knew that there was some weird return at one spot, so there was probably a little crater there. They knew that there was a little bit of an equatorial feature, so they got a really accurate model to the extent that we can, of the shape of Bennu, and it was really cool to get there and then sort of see that match. Um, Arecibo was doing basically up until it couldn't anymore, was doing observations of asteroids, looking for asteroid populations, detecting asteroids, doing follow-ups to see sort of what their spin periods are, how far away they are, if they have other little friends orbiting with them. So it was doing all these really cool asteroid detections. Um, and there's plans to continue doing that with future Arecibo 2.0 potentially, um, and with some additional assets that you can use in the meantime. But it is a huge asset because it can just sort of see differently than a lot of like the optical telescopes that are used to do asteroid studies. And so it's a huge asset to be able to see what's out there and then characterize it a little bit better.
All right, thank you. Yeah, I'm gonna ask my own. I'm gonna keep asking my own questions.
Okay.
So how long do these missions take to get to the asteroid, collect a sample, and then come back? Because you mentioned OSIRIS-X already did the touchdown, but it's gonna be a few years before it does a return. So how long was it for the other Hayabusa missions and total for OSIRIS-REX?
Yeah. So OSIRIS-REx launched in a few years ago. I forget exactly when I went to it. It launched from Kennedy. Um, Maybe 2017. I don't know. Somebody can correct me. But it launched a few years ago, and it took a couple years to get there. Bennu and Ryugu are sort of near Earth asteroids, so they're relatively close, but they are still far enough away and you have to get in the right orbit to get there. So they take usually a couple years to get to, and then about a year or so, once it sort of starts returning, a year to 2 years to get back. And that's based on sort of, again, what orbits they're in, and where other planets are at the time, to try to figure out those trajectories. Um, the planning for these missions started a decade before that, right? So missions have really long lifetimes where you have to plan for a long time, and then you build the spacecraft, you test all of the instruments, and then you finally launch it, and then it takes a little while to get where it's going. You're able to do some science there, and then it takes a while to get back. Missions to like the moon can be faster, so it only takes about 3 days to get to the moon. And so those missions can be much quicker. You can sort of go there and come back in a week, probably a little bit longer than a week for most of them, but you could do something like that. Um, anything going to Mars, right? So Perseverance took 7 months to get to Mars, and that's a pretty standard timeline. So most missions have, and anything further out than Mars is going to take longer. So you have these really long travel times before you're able to get science. And if you want to return anything, it's going to take at least as much time to come back.
Okay, it looks like we have a few more questions. So Kathy's asking, the lunar dust ruined most moving joints on the spacesuits and the rovers on the moon. What have we done to try to mitigate this problem?
That's a great question. Yeah, so lunar dust, as I showed at the beginning, is very jagged and rough. And so it turns out that when you have a spacesuit that's made of sort of a cloth material, and when you have seals between the gloves on the spacesuit and the spacesuit arm, right? They had to sort of lock those gloves in, and those seals got exposed to the dust. The dust is really abrasive, so it rubbed on the spacesuit material, it rubbed on the seals. It had issues with some of the other things that were moving. They had some funny issues where when they drove the rovers around on the lunar surface, it kicked up a lot of dust, and like several of the rovers had a fender break, so they were just getting dust all over the place. Um, but So it's a pretty complicated problem. Partly it's complicated because it's just a really that jagged fine material. Partly it's complicated because of its charged particles also. So if you think of like the way dust sticks to your computer, that's because it's these little tiny grains that sort of have a charge and they stick to the surface because of that. When you rub a balloon and you can stick it to your head, similar thing. Um, so there's lots of work that has been done over the last decade, since Apollo, really. There was a little bit of a break, but a lot of work since Constellation. We were sort of originally going back to the moon. And then now there's a lot of work being done to look at dust mitigation. So how do we avoid getting dust into things. So how do you make seals that keep dust out or that are dust tolerant? How do you make like things to clean your spacesuits? There's a lot of different research into ways to make dust not stick to surfaces. Um, One way for spacesuits, for instance, is you have a spacesuit that you basically leave outside and it doesn't have as many moving parts, but you can sort of leave it outside of your rover or your habitat. So you don't bring dust inside as much. So you have some sort of like mud room or dust room, it would be in this case, right? Where you are able to sort of keep dust outside of your habitat and keep it outside of moving things, but still get in and out of a spacesuit. For things like moving joints and electronics and things like that, we have to find ways to keep it out or to be able to brush it off the surface or use electric fields to move it off the surface. So there's lots of those sort of cool different technologies being tested right now.
Oh, that's pretty cool. Are the particles, I know we're learning that they're bigger, but are the particles on asteroids also similarly charged like the moon?
Yeah, so it turns out that because the moon and asteroids don't have an atmosphere, they're exposed to the solar wind, which is just the charged particles that are streaming from the sun. And it's a plasma, so it's ions and electrons that will hit the surface. And then you also have UV light, high energy light shining on the surface that can kick off electrons from things. And so anything on these surfaces will have charges on the surface. That includes spacecraft, that includes humans, that includes rovers. So any of these things will actually be in this sort of charged particle environment. And so you can get some really interesting natural dust phenomena that happen because of that. And then also both problems and solutions potentially with this dust problem.
Okay, cool. So we have another question from Brian. How significant is the role of thermal cracking in dust formation? And would this bring up issues in eternally dark craters at the poles of the moon and possible landings in them? For example, them
Um,
being too rocky or something.
yeah. So on somewhere like the moon, it's probably not. It doesn't play as big a role because the moon doesn't it has a slower sort of rotation, and so it doesn't have really extreme. Or as the thermal cycles aren't as extreme, right? So the moon, as the moon rotates, if you're in the sunlight, you're really, really hot. If you're in the dark, you're really, really cold. Same thing is true on asteroids. We think these effects are probably a little bit worse on asteroids, partly because they usually spin faster. And so you get these sort of thermal cycles where it gets hot, cold, hot, cold, hot, cold a lot more. You just have a lot more of that cycling. And so if you think about something, if you have like a little crack in a rock, as it heats and cools, that crack will expand and get bigger and bigger, and then it'll eventually break and fracture the rock. And so that eventually breaks down. And we think that it's probably a pretty significant producer of dust on of dust on asteroids. So it actually probably changes from fewer big rocks and more smaller rocks. Um, on places like the moon, it's a really interesting question because we have places like, as you mentioned, these permanently shadowed craters that for hundreds of thousands of years have been in shadows because they're sort of on the poles of the moon, and so they don't get direct sunlight into them because they're down in craters. And in those places, we do think that potentially not just like thermal fracturing of rocks, but the way if you think of something sort of heating and cooling, it kind of settles more. We think maybe there's less settling, it's a little bit fluffier because there's less of this thermal cycling in those craters. So it's possible actually that those craters are a little bit fluffier than the surrounding regions because they don't have as much thermal cycling. So maybe not too rocky, but more fluffy. You probably won't sink in though.
That's the first time I think I've heard the moon described as fluffy.
There's these super cool structures that we think we see from data that are called fairy castle structures. So basically, when you get these little tiny dust grains, they can sort of build up into really loosely stacked structures that have interesting spectral features. So they'll look weird in different lighting, and we think that they exist, but they're called fairy castle because they're like so loosely little things that are just sort of barely stacked on each other and be really, really, really fragile. So those are pretty fun too.
Yeah, almost like a house of cards or something.
Yeah, exactly.
All right, so we have another question from Keith. So we're mentioning the asteroids that these missions that we're going to are near Earth asteroids. What do you mean by near Earth in these
How,
cases?
s- how scared should we be? Yeah, so near Earth asteroids are generally those that are within the orbit of Mars. Um, and so the main asteroid population that's sort of closest to us is in the asteroid belt, which is just outside of Mars's orbit. But near Earth asteroids are generally those classified that are sort of closer in than Mars. There are some that have Earth orbit crossing, where they maybe sometimes go within Earth's orbit. They're generally not going to hit us. There's a lot of space in that orbit. And then there's some that are just sort of nearby, but could. But the reason this isn't interesting, right, is because at some point their orbits could get perturbed and they could come hit us, right? So the gravity from Mars or from the sun or something perturbs their orbit just a little bit, and they go, "Oh, hello, Earth." So that's why we want to study their composition and what their structure is, and all of that. Also, just to understand the history of the solar system, those little things.
All right, so I think that's it so far for the questions. So I want to thank you again. I'm applauding you for on behalf of everybody with us today. Thank you guys for joining us. Unfortunately, we were hoping to do an observatory tour, observing tour with you guys tonight, but the weather didn't cooperate. So please, if you would like to learn more about astrobiology, and actually we do have some moon graphics as well in our interactive space, which is linked at the in the description of the video. Please join us there. And again, thank you, Professor Dove. And we got some comments of your talk was fascinating and the fluffy moon was fantastic.
Excellent. Thank
And for those
you.
of you, if you enjoyed it, please check out the Walk About the Galaxy podcast to learn more.
On all streaming services.